Hey everybody, just want to let you see my face real quick before I jump into some review. There used to be a whole really good video by the guy who wrote our book, and for some reason the AP people took it down. So I'm going to quickly go over the investigative task as best I can and talk about a couple of multiple choice problems that you hopefully did in class today. So I'm going to hide my face and share a screen. Oh, it's there. And let's do this. Let's do the entire screen. Sure. Okay, that's not the screen I want, though. I want this screen. Okay, so you had this investigative task, and once again, the investigative task is a longer one. You should definitely touch it. The idea is you're probably supposed to spend twice as much time on it if you feel like you're making progress. But I think the most important thing is to read through all of it because oftentimes the last question is actually somewhat easier, assuming you've come up with some kind of answer on the previous questions. That's not always the case, but often it is. The other thing is just not to freak out about it because at some point they're going to throw you a curveball and you're going to be like, what the heck? Just keep reading, muddle your way through it, but then don't get stuck. Go back and make sure you're working on everything else. So I'm not going to read this whole thing too, but basically this is some results from a test. There was a pre-test and a post-test after doing some kind of intervention to try to make people's scores go up. And the first question was identify the equation of least squares regression line for the predicting final score from pre-test score. Identify the variables that appear in the equation. So the most important thing here is that you realize, oh yeah, this is the slope and this is the y-intercept. If you go over to the screenshot that I did from the video that no longer exists, they basically say, oh yeah, y hat, which is our post-test score, is equal to 49.28, which is our y-intercept, plus 0.5396x. So that's the equation, but then we need to identify what those are. So the 0.5396, we should say at some point is the slope, and 49.28 is the y-intercept for post-test scores based on pre-test scores. I think that would do it. Let me see if I'm missing. You probably need to mention, say, predicted final scores. It's, okay. And then you can roughly grade yourself here. We're not going to do a strict rubric here. For part B, they asked, consider the information presented in the tables and your answer from part A. Determine the value of the predicted score for students with a pretest score of 65, and then interpret S equals 4.2682. So regardless of what you said for the first one, whatever you set up here, as long as you plug in the X and come up with a value here, you plug in 65 for whatever you said was, and you come up with this, you're going to get a half point here. Hopefully that's what you got. But once again, anything you could have done y equals 2x plus 1 and plug in 65, and you would get half a point here. The other is a little trickier, is you have to interpret this 4.2682, which if you don't know what it is, there's no hope. But what that is literally the standard deviation of the residuals is what I would probably roughly describe it as. But it is how far are the actual data points vertically from the line of best fit. So what they said was the value of S 4.2 is the standard deviation of the residuals from the regression for predicting the final score from the pretest. When the regression line is used to predict final score, a typical prediction error would be 4.2. Those are two possible answers. You don't need both of them. I don't know what's in the rubric. Certainly, you need to say typical, distance from, or standard deviation relative to the line. And you probably need to say, scores, some kind of units, but it's the y distance. So it's a distance in post score from the predicted value of post score on the line. On average, it's the standard deviation. So that's what that S is. That's a little bit, it's a little bit in the weeds as far as what you might need to know. I think more important is that you know what the R square is over here. So this is somewhat weak, 65%. Although the R would be the square root of 0.65. Okay, getting off. Next part. This was hard. Okay, so at this point we are in the what part? So they say The values of both point estimates are equal to the predicted value of the least squared regression. Um, oh, wait, no, there's another part of it here. For any particular pretest score, 2 point estimates can be calculated from the given simple linear regression analysis. One of them is an estimate of the mean final score among all students with a particular pretest score, and the other is a point estimate for the final score of a student for a particular pretest score. Um, Now, we've already calculated it for a student. Um, and so the idea is, well, we could also, this is hard to wrap your head around. It's saying, well, if I use 65, I could also say, well, on average, someone who makes a 65 is going to get this score. These are both the same numbers, which I think what it says on the next page. The value of both point estimates are equal to the predicted value of the least squares regression equation for the particular pretest score, such as from what we just did for 65. Although the value of the 2 point estimates are the same, the sampling variability is not the same. Which of the 2 point estimates has the larger sampling variability? Explain your reasoning. So first of all, you have to take a guess, and then you have to explain why your guess is right. Now, the reasoning here is, oh, well, if I average a whole bunch of scores together, it's more likely to be close to my prediction. Whereas if I just put a single student it's going to predict that same score, but their post score could be wildly different than, for that particular kid. Whereas if I'm averaging a bunch of kids, they are probably going to be much closer to the average predicted score. So that's kind of the reasoning. And this assumes you understand what they are saying back here, which is not easy. But their suggested answer was this. Oh, wait, where is it? It's here. Point estimate 2 has a larger sampling variability. The sampling variability for point estimate 1 reflects how much the value on the least squares regression line for a particular pretest score is varied across all. Now, somehow they introduced 12 here. It's just a larger number of N students. I don't know where the 12 came from. It's not anywhere I can find it. Then they go back and address for sampling variability for point 2 is larger because it's student to student variability in final scores. This is not the only way to write it. I think what I would probably have said, point 2 is larger because for any particular student, their score could vary wildly from the predicted score, whereas a group of students on average are probably going to be closer to the predicted score because standard deviation is smaller for an average. That's the way sampling distributions work. So something around that discussion. And once again, hard question, and I don't know what the rubric would look like. I don't know exactly what you get points for. Very, very hard. Now, this last part, I understand what they said, but they keep going back to this 12. And there's a key word in here that I kind of have ignored because they never told me 12. But they basically say the value calculated is an estimate of the mean final score for all students with a pretest of 65 who completed this course. If a list of pretest scores and final scores for all students who completed the course is obtained, explain how this information could be used to investigate the sampling distribution of the estimated mean final scores of all students with a pretest score of 65. Once again, got to kind of figure out what they're saying here. But what I think they're trying to say is, how could you run a simulation? And if they had said that, I might say, for how many students, which evidently they think is 12. So what they said to do was the sampling distribution of the estimated mean final scores for all students with a pretest score of 65 can be simulated. That would have been a helpful keyword using the following steps. Select a random sample of 12 students from the list who completed the course. Compute the equation of a least squared regression line using the data for 12 students in the sample and use it to predict the final score with a pretest of 65. Repeat the first 2 steps a large number of times. Now that I've wrapped my head around this a little bit more, I see what they're doing. They're saying do this many, many times, and then you can kind of see what the variability is of the. This feels like it's comparing it to the slope. Let me show you what I would have said, which is probably not right, but I'm just going to be honest about. trying to approach this like you. And what am I going to say here? Very often, AP Stats teachers don't know how to do this last problem. And later they realize, oh, yeah, I guess that's right. I don't know how I was supposed to know that. Sometimes they make more sense than others. So what I would have said, which I have typed out somewhere, um, back here. I got to put it down here at the bottom here. Okay, so they said this. I said, this is what I thought. I ignored the investigate. I'm like, they're asking me about the variability of those people who did 65. So I'm saying for the number of students who had a pre-test score of 65, I'm going to call that N. Maybe it's 10 students, maybe it's 12 students, maybe it's 20. If we find the standard deviation of the resulting sample of post-test scores, we're going to call this the sample error, or SC. Then the approximate standard deviation for the mean of all n scores would be about SE divided by square root of n. Because I'm thinking they are trying to figure out if I understand how sampling variability works. That's what I thought the intention of the question was. And then I said, let me plug in some numbers to show you what I mean. So if 20 students scored 65 on the pretest and then got a variety of scores on the post-test, and these scores had a standard deviation of 7, then a reasonable estimate of the standard deviation for the sample means of 25 scores of those who had a pre-test score of 65 would be about 7 divided by square root of 25, 7 over 5, or 1.4. It's not a correct answer according to them. And once again, this is, I think this is a little problematic, but some of them are often this way. I've had ones before where we're like, wow, this is really straightforward. I'm actually surprised it's an investigative task. But the main thing is to just keep reading because maybe that last part will end up being easier. In this case, I don't think it was, but sometimes it is. Let me briefly talk about the multiple choice. So the first multiple choice, they also had a video that described all this, and they deleted it. So the first one, they ask you all these questions about the IQR rule. So here's an example of how to do the IQR. The idea is it's the distance in the box, if the box plot, the distance between Q1 and Q3. And then we're going to go 1.5 standard deviations up from the Q3 and 1.5 down. And I always like to tell my students, visualize the box and add a box and a half onto the top end of the box and a box and a half to the bottom end of the box. And that's roughly where your outliers will lie. So if you calculate these like this, or I did it in Desmos, so I'll show you what it looks like in Desmos. I subtracted them and I multiplied it by 1.5. So that's the amount I'm going to add on to get a 3.755, and I'm going to subtract off of the Q1 to get 1.4, which I think is exactly what they got. It is. And all the questions are related to the minimum and maximum about whether they are outliers or not. And none of them are outliers, which is why the answer is E. The other answers are, let me pull it back up and I will go through them quickly, hopefully quickly. And you can stop this anytime you like, or you can fast forward. That's not it though. It's in a different thing. It's here. Okay. Okay, we just did that one. Okay, number 2. Tail of a Siberian tiger is approximately normally distributed with mean of 0.85 and a standard deviation of 0.13. Which of the following is the best interpretation for the z-score of a Siberian tiger with tail of 0.08? Now you could draw a normal curve, but I really need the z-score first. So my z-score is, normal curve is not going to help you. I'm going to do, there it is right there. 0.8 is my score. 0.85 is the middle of the graph, and the graph varies by 0.13. Now, I could now put this in a normal, but that's not the question. I don't need a normal curve. I could do a normal curve, but it's basically what does that, what is it and what does it mean? It's negative 0.38. And so that means the tiger's tail is approximately 0.38 standard deviation below. I didn't even read the other ones just because I knew the top one was right. It's good to read the other ones just in case you might notice something later on. Wait a second, why did they say that? Or why is this wording almost identical to that wording? If the first one was above and you didn't notice, oh yeah, below is further down. But that one is definitely A. Okay. This one is hard. Because if you don't know what power is, it's a little problematic. So I've got a picture drawn. in the form, which I'm going to show you again. Um, the basic idea is power is the ability to detect an alternative value, which means you have to have a null and you have to have some alternative value that, well, I think this is the real value, which is a little weird to begin with. But the idea is, I'm going to believe the null, which we never say. We're going to say we fail to reject the null, but I'm going to believe it until I get into my rejection range. So the idea is until I get out to the 5% out here, I'm going to believe my null, whether it's true or not. So if I get out here, I'm going to reject the null. Now, if the null is true, I have just made a type 1 error. But if the null is false, that's great. I actually want to be out there. And if my true value is out in this other curve on the right, I'm hoping I land closer to this curve. So anywhere in this curve that I land that's beyond my alpha area, that's my power. The area under here is how likely am I to correctly identify a, um, a an alternative value, which I have to know ahead of time. And that's often called the power. And this area in here, that's the tail of this alternate value. Because once again, even if the alternative value is true, I might fall in the tail, and I'm going to believe that the null is true, which I never say. I say I failed to reject it. But the idea is if I fall out there, that's what's called beta. Um, that's a chance of a type 2, because that means I rejected the alternative, or I failed to reject the null, even though it's true. Even though it's false, sorry. All right, so that's just the setup. The question is, if I move this 0.05 over to 0.01, and there's a typo down here, it says moving 0.05 over, I should say 0.01, we're going to make the type 1 likelihood smaller because it's less likely I'm going to be in the tail, and in the tail is where I make a type 1 error, assuming the null is true. And it's going to also decrease the power because as I shift this thing over, this area over here gets smaller and smaller and smaller. It gets a little harder for me to land over here. I've got a bigger tail on the alternative if it's true. So C is the correct answer. Don't get hung up on power. It's nice if you know what it is. There's a chance you might get a power question, but it's not likely. The probability is low. Then finally, let's see. This one right here. Um, I actually had a error in my key last year and nobody noticed it. The only problem with this one, we're just trying to do a confidence interval. We know the middle of our thing's got to be 42.1, so the A doesn't make sense. I'm doing plus or minus some value. Notice it's a 90% confidence level, which you have to remind yourself, oh, that's not 1.96. It's 1.96 times something is 95%. So I have to either figure out what that is or look it up. Um, I don't know if I'm going to quickly see if I can't figure out how to do this with Desmos, just in case I need to remember how to do a 90% confidence interval. I don't know if I can do it. This is dangerous. I haven't tried this yet. No, inference, probability distribution, z-score, um, 0, 1. This is our standard table. Looks like this. And I am trying to figure out the outer. I want to be, I want that to be 90%. Okay. That says 1.26 on both ends. Oh, why did I think this was going to be 1 point? Okay, we're going to check the table now because now I'm wondering, wait, maybe there wasn't a mistake here. This is saying, wait, oh, wait, no, I'm doing it backwards. There we go. 1.645. Okay, I got the right number. Whew. That's the problem with using this. If you don't know how to do it or you don't have some idea of what you're supposed to be doing it, the table's easier. If I'd use the table, which I'll just remind you of, no, I don't want to do it. Do it here. If I was using the table, I could, the easiest way is to go to the bottom of the T table and say, oh yeah, 95%, there's our 1.96, which everybody has memorized. Oh, and there's 90%, which is 1.645. And in case I need 99%, which is the other number that I might need, it's 2.576. Okay, so the way that I did this is I know it's going to be 1.645 The standard deviation was 3.6, and there were 25 of them. So I have to either remember that formula or probably, just to make sure I don't make a mistake, I probably want to check my formula sheet to remind myself that that is how we calculate the standard deviation for a population mean. Okay, so that's 1.1844, which is why the answer there is D. Um, Not going to read this whole thing, but basically the idea is this is the data we have, and one person says, I think the number of absences for every day of the week is equal. Somebody in HR says, no, it's not. And they come up with this data of 150. If it's 150, each one of these days should be 30. So they are clearly all off. The Tuesday and the Thursday are pretty close. 28 is closest. And I could do a whole chi-square, but they didn't ask us me to do a whole chi-square. They just asked me what would be the contribution of this. So the idea is, oh, if each one's supposed to be 30, the difference there is 10, the difference there is -3, the difference there is -9. But a contribution, which is also on the formula sheet, by the way, it's on the front page, chi-square, observed minus expected divided by squared divided by expected. So that's if I sum up all of them. I'm just asking for the first one. So that's going to be my 40 minus my 30 squared, which is going to be 100 because it's just 10. But then I got to divide it by what was my expected value, which was, 30. This is 3.33. And I think the correct answer is on the key. It should be D there. We're going to go back and check because I did this earlier and I wrote down 2.5 because I was dividing by 40, not by 30. So let's make sure the key is right. Is the key correct? Key. D. Yeah, key is correct. But I had picked the wrong. I went through these ahead of time. Let's see. Is there anything else? Oh, just for fun. Let me show you how to do this in decimals. So we do plus if we were asked to do the chi-square inference. I could do it manually, but I can also do it. This is for, I'm going to say it's for goodness of fit. So our expected is, observed is 40, what was it? 27, 21, 21, 34, 27. Now, if these aren't all expected to be the same, we should fill them in. But because they're all expected to be the same, it will figure out for us. But if we had different expectations than all of them being equal, we need to put in what those expectations are. Great test. And we can see that those are our numbers. There's our contributions for each one. So, did I type something in wrong? Because this is not saying 3.33. The last one was 28. Let's fix that. It's like, it's a little bit off. There we go. Perfect. And then I can actually say, oh, my chi-square, my p-value is 0.13. So that's not particularly large. If we were going to do a chi-square test, the assumption is that these things are all the same. This is not small enough for me to reject the it feels like they're quite different, but they're not different enough for me to reject it. Notice also my degrees of freedom there is 4 because there's 5 items in the list. A little surprised the p-value is that high. I would have thought it to be a little lower because it feels like these are pretty far off, but guess not enough. Okay, that was probably way longer. I doubt anybody's stuck with me for this long. Let me just stop sharing so you can see my face one last time. Stop sharing. How do I stop sharing? Oh, I don't think that's it. Maybe I won't. If I can't figure this out, I'm just going to say goodbye. Yep. Goodbye. Ciao.